Greetings and welcome. I am Kshitij Doshi, and with me is my colleague Harshad Sane. Today, with highly interactive chains of services powered by real-time AI, both low median latency and tight latency control are key needs in many application domains. While achieving low median latency is a complex engineering challenge, ensuring tight bounds on peak latency is a difficult level of difficulty altogether, and we would like to describe how hardware assisted monitoring can play a role. We decided to split this flow into two parts. First, in the next few minutes, let's talk about some of the subtleties of managing tail latencies. After that, we will turn to tackling the challenges in the second part of the flow. Now, it's very often the case that in order to get to tail latency, we have to understand the causes. And the typical expectation is that in order to focus on causes, we have to look for things that are causing load spikes or errors or failures, and then resulting in excessive amounts of latencies. However, the reality is that very often the causes of tail latencies lurk in plain sight, and furthermore, their effects are conditioned by various other catalysts that are completely innocent in nature. So, as a result, it's very often the case that uh, we have to look for we have to look for very atypical events that happen to last only a very short amount of time, and standard approaches that we use today in order to expose throughput limiters do not generally expose the causes of peak latency. And let me just give a couple of examples. Suppose, for example, that there was an iteration that just took a long time in an atypical case as a result of needing to converge on a value. And let's say that the results of that iteration, that sequence of iterations, were feeding some pipelined stage in software downstream. Then the thread that was executing that particular pipeline stage might get switched out while waiting for the latest data to arrive, and then may take a while to get scheduled back on the CPU, and thus the latencies can build. Alternatively, imagine that the amount of work to be done does not change very much from iteration to iteration. However, it's possible that some particular request happens to present a different enough data access profile that cache misses or page cache misses go up, and as a result, latencies widen and once again precipitate downstream effects. So these kinds of things can happen at extremely small intervals of time. Let's use an illustrative scenario that we encountered recently, and it shows yet another example of various kinds of transition events. Here we have a latency critical event workload in which, as the throughput increased, the tail latency happened to cross this particular time very early on, and an SLA violation occurred. Now, when subsequently this was corrected by fixing whatever the problem was, as you can see, the SLA violation point moved further to the right and closer to where the throughput was maxing out. Now, why was this happening? It turned out that the main cause was that the default power settings were putting the system in deep sleep state at low loads, and as a result, the SLA violation was occurring much earlier. Now, when this was fixed by changing the default sleep states into something that would be a minimum sleep state, then the processor would not go into deep enough sleep states, and therefore the circuit level realignments in various timing loops would not take so long in order to come out of such deep sleep states, and further the caches wouldn't get as cold. Now, this was a situation that poses an irony in that the effects of either of these sleep state settings on median latency are not particularly critical. However, the low utilization results precisely in the early onset of peak latencies because of encouraging the transition into a deep sleep state. Let's talk about a different kind of transition in a second scenario. Here we are going to be talking about effects of process schedulers. Now, typically, a thread scheduler or a process scheduler in an operating system has to deal with a lot of different kinds of situations where it has to ensure that thread migrations are kept to a minimum in order that threads can benefit from the soft affinity that they build up and get warm cache effects. Now that has to be balanced against the fact that if some thread is ready to run because it has been woken up from a sleep, but the CPU on which to which it is currently attached happens to be very busy, then it may not get that scheduling interval for a long time. And while there may be other CPUs in the system that may be going idle for lack of work being assigned to them. So migrations have to be balanced against that kind of soft locality. Another example is when some thread gets woken up and now if it has been sleeping for a while, then ideally it should be scheduled on the CPU quickly enough. But if we were to preempt the threads all the time in order to reduce the time after wake up in order to get scheduled, then we would end up increasing the overheads that are taken up by the scheduler, as well as increase the cache miss rates. Now, the workload that we were dealing with here was a gaming workload where the importance was to get a high enough rate of frames per second, and that meant that it was generally important to achieve a reasonable amount of hotness in the processor caches, especially the level 1 and level 2. Now, this poses a little bit of a tension between preempting too soon, where we are not allowing a running process to build up and benefit from its own cache warmth, versus meeting deadline priorities, which is important to schedule quickly upon waking up. Now, it turned out that the solution in this particular case was to adjust a couple of Linux CFS scheduler parameters, essentially in order to encourage migrations over cache affinity. Now, that is not an absolute one. So, if a thread got woken up, but the thread that was running currently had not yet built up enough runtime, then it wouldn't get preempted, but otherwise it would get preempted fairly aggressively. And the code snippet below explains this from the thread scheduler in the operating system. So the upshot of these two types of transitions related latency points is that very often it is the sub-millisecond effects, right, that have an outsized effect, and thus small time ranges contain the vital signals for analyzing tail latency growth. When we look at what happens today, however, in classical profiling, is that if we were to collect all of these events all the time in order to pinpoint where exactly it was that the latency adders were coming into picture, then the overhead in terms of CPU activity and memory activity would be prohibitive. So instead, sampling and averaging of CPU is a very common technique in order to collect program counters and identifying where is it that the programs are spending a bulk of their time, and then tracing it back to seeing whether at a point when a tail latency crossing occurred, whether there was a significant change in the profile between the median case and the case when the tail latency crossing occurred. But as we have described before, these kinds of effects tend to be very short in at the time of their occurrence, but they have longer duration of impact. Now, if we were to look at a second problem, right? So in this scenario two, we were collecting. Let's say that we were able to observe all of the intra-process and inter-process scheduling effects. Um, we would still need to do that more or less continuously. In the first scenario, that was not an issue because one could say that uh, uh, the entry and exit into sleep states is a rare enough event that it can be collected and can be time aligned. But in case of schedulers, right, the granularity at which these effects occur tends to be very small, and therefore these kinds of events have to be collected and correlated on a more or less continuous basis. So we have just walked through a set of subtleties, and let's turn to an examination of some of the software techniques in the solution space, and then the role of hardware in supporting those techniques. So the first tool that we would like to discuss is perf-sched, which is a dump and post-process approach for capturing and analyzing scheduled events. So it's a tool that is very versatile, captures a significant amount of information, but at a sufficiently low overhead that it is very useful complement to the classic performance data collection tool on Linux called the perf. With perf-sched, one can collect a trace of various scheduler events as shown on the right, and get to an understanding of how far is the scheduler delay, that is how long it took for a thread that was just woken up to be assigned a CPU. Equally, how long did it take for a thread to be woken up from the point that it went to sleep? And then furthermore, in its time history, one can check when is it that the maximum amount of scheduling delays occurred, and so one could at least in principle get an understanding of the timeline over which a number of these high latency contributing events occurred. Now, when this is happening, one would also be able to see what were some of the other contemporaneous activities that were going on, so that even if they are not perfectly time aligned, they provide a context within which these kinds of delays are occurring. Here is a another view of perf-sched with a better visualization in terms of various kinds of migration events. There's annotation there, and one thing that I should mention is that perf-sched also collects the fork and exec history, so that it can correlate when is it that a particular thread forked and then exec a different command, so that the same process at two different points in time in the history, right, can be understood to be subject to the various kinds of delays that are shown here. And another tool in the same vein is KUtrace, which is a very carefully designed engineering tool for measuring uh, the various kinds of time delays by collecting uh, all of the kernel to user and user to kernel transitions of threads at extremely low space and time overhead. Now, when collecting these events, what DigSites does is he also collects a significant amount of ancillary data. He collects, first of all, the reasons for these transitions. They include system calls, traps, page faults, disk wake ups, network wake ups, and so on. He also collects enough information in order to correlate, let's say, the call return pairs that occurred in the context of a system call or some other messaging interaction, so that it is possible to correlate for a given thread all of its activities uh, uh, precisely by looking at all of the transition points that it went through. Now, in addition, he also collects the IPC at these various kernel to user and user to kernel transition points, so that it's possible to look at a thread's history, divide it up in terms of various intervals over which it is possible to see when was it that the process was running at high speed, and when was it slowing down by several factors or even orders of magnitude. And all of this is done at a very small overhead of about uh, uh, 32 bits per event, and at 40 nanoseconds overhead, which is compared to even the event itself significantly smaller in magnitude. Thus, it's possible to use some of these tracing tools that we just looked at. Now, let's look at some of the capabilities that the hardware providers are bringing to the party. Modern CPUs have an amazing ability to capture many different kinds of events, and do so at very low overhead through the ability of a separate hardware circuit called the performance monitoring unit. Now, this performance monitoring unit, or PMU, has a wide variety of different settings. It dedicates a certain number of event registers in order to either count or generate count-based, that is, event-based samples by which one can collect profiles that are predicated on some regions of code or some regions of data being rich in certain kinds of activities. Now, all of this is done at very moderate granularity, and because one can collect a lot of this information with event-based sampling, it is possible to collect a lot of correlated ratios along many different dimensions, and allow an examination of what could be causing various kinds of IPC shifts. We would like to talk about a couple of interesting PMU capabilities that not everybody may be familiar with. Uh, the first of this is timed last branch records. Last branch records are a way for the hardware to automatically collect the sequences of different branches that various basic blocks have experienced between them in the context of a continuous execution of a thread. And then when one samples on the basis of these last branch records, one can create a path profile, that is, how often do different branches get traversed, and therefore how often do different paths get traversed. Now, what timed LBRs do is that they associate along with these last branch records fine-grained timestamps by which it is possible to see how time dilations occurred across these different paths, And so one can set up a sampling type of event-based sampling type of technique, so that one can collect a kind of a path graph that is annotated with the total amount of time delay on a statistical basis that builds up along a particular path. So this is an example of something that we have been able to construct with timed LBR based instrumentation. Perf, for example, provides for this kind of capability, integrating timed LBR based snapshots. Another capability in the same vein that folks may be aware of or not aware of is the ability to identify various kinds of data hotspots in addition to the code hotspots or code path hotspots that we just walked through. Shown here in the blue is a code for how one might collect memory transactions that upon completion had required a latency that was greater than some threshold number. So with that threshold number, one can profile various kinds of latency ranges. For example, latency ranges of 4 to 7 or 8 to 15 clock cycles, right? It's at that small a granularity, right? In order to typically capture things that missed the L1 cache, or how often did things miss L1 cache. Um, uh, and how often did they miss the L2 cache, and so on. So out as we go to 1024 or 2048 cycles of latency, we are really targeting those that rare species of data accesses that are missing not only all the caching levels, but have been slowed down even in their response from DDRs, because either they went to a different socket, or there was a very high level of bandwidth utilization which pushed this particular request out in time in order to be satisfied. So what happens is that when we collect these kinds of samples, we get both the code address at which these kinds of events occurred and the data address that was in question. Thus, one can get a two-dimensional view of which are the places in code that are experiencing large amounts of data access related latencies, and which are the data items that are being referred to. So this should give an idea of all of the different kinds of complex types of events that hardware makes it possible to sample at very low overhead. And today, what that means is that there is an opportunity to combine the kinds of tracing that we saw with perf-sched and KUtrace with the hardware-based sampling in order to pinpoint what might be the causes for some of these latencies that are showing up in scheduler graphs or time-based graphs. Now, the challenge, however, is that one has to intermix the collection of various kinds of profiles with the triggering events on the basis of some kind of analysis, and that analysis typically has to um, uh, go through the data that was already collected and dumped, whether it was by KUtrace, perf-sched, etc. and and again the same dilemma presents itself. If you were to instrument everything, then not only are you having a significant amount of CPU penalty from over collecting and memory and cache pollution, but you also have a lot of data to go through. So these are some of the challenges that have to be reconciled, and they have to be reconciled with particular attention to the fact that it can't take a very long time in production environments. Otherwise, these kinds of tools are only to offline, and that to repetitive exercises in trying to reproduce something that is very difficult to predict. So one capability that is certainly very useful, and that other presentations at P99 are touching on, is the eBPF, or Extended Berkeley Packet Filter capability. It provides a programmable triggering and conditional collection at low overhead, because we are able to have application driven or application software driven or a cohort driven um, automation with eBPF, in order to sample things, whether they are occurring in user space or in kernel space. So even if we were to just look at the two examples that we looked at from for the two hardware capabilities that we talked about, um, one can use eBPF based triggering in order to combine them both, so that on the one hand one can use longest latency access event based sampling, which is the timed LBR event based sampling, as a trigger in order to snapshot the I'm sorry, the other way. One can collect a significant amount of longest latency access events based sampling, and then use that as a trigger in order to collect a snapshot of what was in the timed LBR buffers, so that one can see not only where these longest latencies accesses are occurring, but what was the time history of the thread that came through and was in the vicinity of those kinds of long latency accesses. This then can be extended to other to integration with other software-based tracing tools, so that one can leave KUtrace or perf-sched to do what they are very good at doing. They're intentionally austere tools that are designed to do one thing and one thing very well, so that it can be so that these tools can be deployed in production and collect the kinds of flight recorder data that is important to identify when things of interest should be looked at. And then with eBPF, one can zero in very quickly on collecting the samples that can be used to annotate what else was going on at the time that those long latency events occurred. And um, so with eBPF control tracing, we could then focus on the just-in-time nature of collection. That is, focus only on areas of interest rather than focusing on everything. Uh, uh, One can, for example, trace all gRPC requests with packet sizes higher than, say, 64K, because one wants to focus on some latency dilation events that are correlated on a time basis with this particular event as a this particular factor as a possibility. The other thing is it's also possible for such triggering to be dovetailed nicely between hardware and software, so that with eBPF one can direct both hardware and software collection, and at the same time activate those things that have a significantly high overhead to be only undertaken exactly when the rare events that require the information furnished by those events to be available. So to sum up, tail latency control is crucial. Increasingly, everything is becoming interactive, and so we want to be able to ensure that peak latencies are monitored, ideally even in production systems. And that means that low overhead and agile monitoring of latency excursions is needed. Now, at the same time, we need the ability to do conditional collection and filtering, for which eBPF is eminently useful, and that can then be aligned with hardware performance monitoring capabilities, which are available in modern processors. They are rich. They can collect a very large variety of events at very low overhead, and by linking those two capabilities, one can go for monitoring of complex sequences of events that cause uh, uh, excessive amounts of latency buildup in a few crucial places, exactly close to where they occur. And because we do triggering of hardware event rate collection with eBPF, we can also reduce the amount of time that has to be spent in analysis, and very often reduce the amount of data that needs to be looked at for analysis as well. And uh, uh, ideally, right, all of this would be collected in a dovetailed manner with various kinds of counters or probes placed on wait signaling and post wait dispatching events. With that, I would like to thank you for your participation here, and we would love to hear what questions you may have, or what thoughts you may be sharing with us in the speakers lounge.